Of course, we're all waiting for the directional derivative shortcut, so here it comes. Let's assume we're looking at a function of x and y, a function f that produces dependent variable values z, and let's also pretend like we have a line in the xy plane given by the parametric equations that I have here. If we plug the parametric equations, so replace x with a plus h times u1 and replace y with b plus h times u2, if we plug those into our function f, then we can create a curve along the surface that travels above that line in the xy plane. So essentially, z would look like a function of h. u1 and u2 would come from the components of the vector that's parallel to the line we're using. In other words, there's some vector u that has components u1 and u2 that we used to generate that line. So in this case, they would just be a constant. The only thing that's changing is the h value. And looking at z with this substitution done, we can see that now we're able to find how z changes with respect to h. Using the chain rule, we would say, let's find the partial of z with respect to x times dx dh. Also find the partial of z with respect to y, dy dh. And if we look at this here, dz dx, or partial z with respect to x, partial z with respect to y, and then we match up the other partials, dx dh, dy dh. Well, the dx dh, dy dh, that actually looks like the derivative vector for the line that we're looking at. So if we wrote that as dx dh, comma dy dh, and we wrote it as a vector, we can see that this looks like it came from a dot product. So we've got the partial derivatives going into their own vector. If you were to compute the dot product that I have written here, you would get the same thing as the line that's right above it. So we're just kind of reversing this. We did a substitution where we plugged the points along the line into the function f to generate a curve on the surface. Kind of like the green line that I showed you in the pictures from the last video, the intersection of a plane and the surface. That's what we generated with the substitution. Then we said, well, we can use the chain rule to find how z changes with respect to h. We applied the chain rule. And then from there, our wheels started spinning and we said, well, this actually looks like it could have been a dot product between two vectors. Looking at it that way, we can see that dx dh, looking back at the definition for x, it's actually just giving us the u1 component. Dy dh, that would just give us u2 component. So we're just taking the derivative of the x and y equations that we started with to find u1 for the derivative of x with respect to h, u2 for the derivative of y with respect to h. And then we're seeing that we're essentially dotting that with a vector filled with the partial derivatives of z, all the possible first order partial derivatives of z. So we just found our shortcut. Rather than doing the limit definition of the derivative, we are using this idea that we can substitute all of the points along a curve into our original function for the surface, apply the chain rule, and then deconstruct that chain rule into a product, a dot product between two vectors. One of the vectors is the direction you're calculating the derivative in. The other vector is something new, something we haven't seen before. This is a vector that contains all of the first order partial derivatives as each component of the vector. And since this is showing up as our next step in the shortcut of a directional derivative, we think it's pretty important, which is why it has been given the name the gradient vector. The gradient vector uses an upside down triangle along with the name of the function as its notation. So this is a new vector for us, the gradient vector. The gradient vector is composed of all the first order partials. So let's put that as a note over here. The gradient vector contains all first order partial derivatives. So if we're looking at f of x, y, then the gradient of f is the vector containing the partial of f with respect to x, as well as the partial, of y with respect, dang it, typo, partial of f with respect to y. So if our function is f with independent variables x and y, we're going to have a partial for each independent variable. What if we had a function that depended on x, y, and z? Good question. That gradient vector would then have three components. We'd have the partial of f with respect to x, partial of f with respect to y, and then lastly, partial of f with respect to z. So every first order partial is a component in this gradient vector. So this is excellent. In order for us to find a directional derivative, all we need is to know what direction we're traveling in, that's u, the u vector, and the gradient vector. There's one caveat. If the direction you're traveling in is not a unit vector, you should normalize that. Because when we talk about the rate something changes, we like to talk about it as a unit rate rather than saying, oh, I get 37 miles every 3 gallons of gas. Nobody wants to communicate rates that way. I want to know how many miles can you drive on 1 gallon of gas rather than how many miles you can drive on 3 gallons of gas. So the direction you travel in, a vector u, you should use a unit vector. If it's not a unit vector, normalize it, turn it into a unit vector, then apply the shortcut. The shortcut is def is equal to the gradient vector dotted with your unit vector. Piece of cake. You don't have to do the limits. You don't have to do a ton of algebra. You may have to take multiple partial derivatives, but we've been doing that for a few semesters now, so derivatives shouldn't be a huge hang-up for us. Let's try one. Using our shortcut, finding the gradient vector, dotting it with the direction we're traveling in, let's calculate the directional derivative for this function, f. F is equal to x times e to the y plus cosine of x times y. So first thing we need to do is find our gradient vector. We know that the gradient vector contains the partial derivative with respect to each variable, so I'm going to find two partial derivatives here, one with respect to x, one with respect to y. The partial with respect to x would look like e to the y minus sine xy times y. Partial, I keep writing that wrong. Don't make that mistake. Partial of f with respect to y would look like x e to the y minus sine xy times x. So our gradient vector contains those two components. The partial with respect to x. I'm going to write the y in front. I like that better. And then the partial with respect to y. Cool. We also need to check that our vector that we're traveling in the direction of is a unit vector. To figure that out, we'll take the magnitude, see if it's equal to 1. Square each of the components, add them up, square root them. That will simplify down to 5. The magnitude of the vector v is 5, therefore it is not a unit vector. Unit vectors have a magnitude of 1. So we're going to create a unit vector in the direction of v by dividing v by its magnitude. So we'll get 3/5 in the I direction, 4/5 in the j direction. So in order to calculate the derivative function, we would do the dot product between the gradient vector f and the unit vector u, but we are actually asked to calculate this at the point 2, 0. So before we do the dot product, let's evaluate our gradient vector at the point 2, 0. So all of our x's will be replaced with 2, all of our y's replaced with 0. E to the 0 is equal to 1. 0 times anything is 0, so our first component is just 1. Our second component looks like 2 minus 2 times sine at 0. Sine at 0 is equal to 0, so that simplifies to just be 2. So our gradient vector at the point 2, 0 is the vector 1, 2. Now we can calculate the directional derivative at the point 2, 0 by doing the dot product of f, the gradient of f, at 2, 0 with the unit vector in the direction of v. In other words, we're dotting the two vectors that we have. Whoops, wrong kind of bracket. Dot product says multiply corresponding components and then add them together. And we get 11/5, which we can interpret as for every 1 unit we travel in the direction of v, the surface increases in elevation by 11/5. So this is an example of calculating the directional derivative using this shortcut with the gradient vector dotted with a unit vector in the direction for the derivative which you're calculating.